Welcome back, everybody. Today we are going to talk about forces and fields. In past videos, we've talked about the electromagnetic force and how it only acts between charged particles. And we've also talked about how it's more complex, how it depends more just on the magnitude of the electric charge, but also on things like acceleration and velocity. One of the things that I think is really cool about the electromagnetic force is that it is everywhere and it explains a lot. For example, take the atom here. We've got a nucleus with neutrons and positively charged protons, and then we have electrons here orbiting. And there is an electromagnetic force of attraction between the electrons and the protons. And so much of chemistry is the result of the electromagnetic force interacting between charged particles. It is literally everywhere. So you might be wondering, why is it that we call it the electromagnetic force? So it turns out that you can actually take the electromagnetic force and break it up into two parts. So if you have a charge Q here, and it's experiencing a force due to the electromagnetic force, you can break it up into an electric component of the force and a magnetic component of the force. So you might be wondering, why don't we just say that we have two different kinds of fundamental forces, the electric force and the magnetic force? Well, as you will find out later in this course, electricity and magnetism are very much interlinked and interconnected. And you really just can't separate the two. So that's why we just say it is one force, and you can decompose it into an electric component and to a magnetic component. The electric force specifically depends on the amount of charge that you have, and the magnetic force depends on the velocity of the charge. Up until now, we've been talking about forces, but now what I want to do is I want to introduce the concept or the idea of an electric or magnetic field. So sometimes when we are solving electromagnetics problems, we don't really want to know what the force is on a charged particle, but we want to know what the force would be if we did place a charged particle at a certain point in space. And it's this concept of a field that we use to be able to predict exactly this. For example, suppose you pick a point in space and you happen to know that at this particular point in space and time, there's a certain electric field and magnetic field. Well, if you were to place a charge Q at a certain point in space, and you know it's electric field, all you have to do is take the magnitude of that charge you put there, multiply it times the electric field, and you would get the electric component of the force on that charge. In a similar manner, if you place that charge at that point there, and if the charge is moving, if it has a velocity, then it will have a magnetic component to the force, and its value will be equal to the magnitude of the charge Q times the velocity of the charge crossed with the B field vector. And so then if you were to add those two forces together, you would get the total electromagnetic force. So let's talk about the idea of a field in a more mathematical sense. Basically, if you have three-dimensional space here, a field is basically some sort of quantity that is a function of three-dimensional space and time in general. So there are two different kinds of fields. One is the vector field. The vector field basically assigns a vector to every single point in space. So this could be like your electric field, for example, at this specific point in space. And it's a function of basically this position vector r. R is basically just tells you where you are, like your XYZ coordinates there. But each point in space has a certain, a vector with a certain magnitude and a certain direction. And so we can say it's a function of the position in space and a function of time. And you can say the same thing with the B field. Now there's also the scalar field, and a scalar field is where you have a function or quantity that's a function of the r vector here, the position in the coordinate system, except it's not a vector, it just has a magnitude. That's called a scalar field, and later in this course we will be dealing with some scalar field quantities. And again, just to reiterate here, this r vector here is just the position vector. It's just a way of denoting the position of the point that we're trying to designate in space, which is just going from the origin to the designated point. All right, so now that we've introduced the concept of a field, let's go ahead and apply that to a simple case. Like, for example, can we come up with a formula that describes the electric field coming from a point charge Q? Well, we know from Coulomb's law that if we have a charge Q and we were to then insert another charge a distance away, we'll call it Q test, then that Q test would experience a force, and we could calculate it just from Coulomb's law here. So it turns out if we know, though, that force that this charge experienced when we placed it there, we can then use our definition of an electric field to find out a formula for the electric field. So we take that charge or the force on that test charge that we would measure if we placed it there, and then divide it by the Q test, and we end up getting this expression over here. So basically, you can say that the electric field from a point charge is equal to this whole expression here. And I also just realized I forgot the r hat unit vector there. But basically, you can think of the electric field as emanating radially or spherically from the point charge.